Now we'll discuss today's class. Let us discuss effect of wind and ice. You are looking at the diagram. You know the effect of atmospheric conditions on transmission lines. Here, the performance of the transmission line gets affected by the atmospheric conditions in the areas through which it is running, wherever it goes, wherever it runs. If it is running through the area where winter is very, very severe and the area experiences a snowfall, then there will be ice coating on the transmission line that everybody knows. Such coating increases the weight. Similarly, in hilly areas, the transmission line gets subjected to tremendous force of wind. Such widely varying conditions must be considered while designing the transmission line and also in calculating the sag and the tension in the line of the conductor. In the line conductor, see, we will study now the effect of two severe atmospheric conditions on sag under tension. These conditions actually now I have already shown here. That is, one is ice coating and other one is wind pressure. First diagram deals with ice coating. You are looking at the diagram. When the transmission line is coated with ice, the thickness and size of the conductor increases. That is definitely everybody knows. This thickness actually depends on weather conditions. This causes increase in weight of the conductor. Of course, it increases this weight, increase in weight, increases the vertical sag. It sags down vertically because of gravitational force. You know that, everybody knows it. The weight of ice acts vertically downwards in the same direction as that of the conductor. Now, let us consider a conductor with diameter d. I have shown in the C. Please look at the diagram properly. Consider the diameter d. It has, okay, it is coated with ice. The thickness of ice is shown as T here. Hence, the overall diameter of the coated conductor is increases T plus D, correct? T plus D. Let me call that as capital D. Okay. Now, here, this D is nothing but T plus 2T. The area of the coated conductor is pi d square by 4. Applying that relations, I have got weight of the conductor per unit length. See, this is effective of ice. Next, second diagram is effective of effect because of wind pressure. Let us see what happens due to wind. That also have to consider. Finally, I will tell you what is the weight of the conductor per unit length The wind actually flows horizontally. I have shown in the diagram here wind force. I have shown wind force. The circular is circle which is there. That is nothing but a conductor. The wind flows horizontally. Therefore, wind pressure on the conductor is considered to be acting perpendicular to the conductor. Thus, force due to wind acts at right angles to the projected surface of the conductor. You can see that it's shown properly. This wind force, I am calling it as WW. I have written to the right side of the diagram WW, which is acting vertically. It is horizontal force. WW, wind force per unit length. It is always measured in kg per meter. This is nothing but wind. That wind force is nothing but pressure into area. Wind pressure per unit area into projected surface area per unit length. So wind pressure into D plus 2T into 1. Together, WW, the force will be P into D plus 2T. Hence, the conductor get acted upon by two additional forces. One is vertically downwards, Wi, and one is horizontal direction, WW. That is shown here. The effect of ice as well as wind loading together, the two added the weight on the conductor. How it is considered? W, weight of the conductor itself acting vertically down. Wi, weight of ice acting vertically down. WW, wind force acting horizontally. Hence, the total force acting on the conductor is vector sum of the horizontal and vertical forces. That is in the diagram I have shown here. Thus, the total weight of the conductor becomes, which I have written here, Wt is equal to root of W plus W the whole square plus WW square. Hence, it is necessary to note the following points. The sag direction is at an angle theta measured with respect to the vertical. Hence, the sag is called slant sag. This is calculated by the expression derived earlier considering the total weight Wt. Okay, now this one here, density of ice, we have got the wind loading and also ice loading. Wind load, ice loading is nothing but density of ice into pi t d plus t, whereas wind loading is d plus 2t into 1 into wind pressure. So totally the sag in the total, this one, the conductor adjusts itself in a plane which is at an angle theta with respect to this vertical. The angle is given by tan theta, which is equal to WW by W plus WI. As a slant sag S is in the direction at an angle theta with respect to vertical, the vertical sag is cosine component of the slant sag S. So vertical sag we will call it as S cos theta. Vertical sag is. So this completes effect of wind and ice loading on transmission lines.